Hi, my name is Matthew Goldenson, and I'm the director of the Business Solutions team. And our team's responsibility is to create benchmarks that are representative of customer workloads. Let's talk a little bit about the array first. The array is what we're working with today is a 3-node Invicta. We have 2 storage routers at the top, and underneath that we'll have 3 separate storage nodes. So what we've done is we've created an environment where the applications will share all 3 nodes. So for 2 of the applications, which are SQL-like, what we've done is we've carved out 3 15 gigabyte LUNs across all 3 nodes. So 1 server, 3 nodes against all 3 devices. Second server, also 3 nodes, shared with the other 2. And then the last one, also shared, will be a desktop boot storm where we will kick off simultaneously 600 desktops. So a little bit about the workloads. The first workload that we'll kick off will be representative of an OLTP or a heavy OLTP application where SQL Server would be doing lots of write activity. You would have lots of users all actively working on an application and executing transactions against the database. So typically in that environment, that's lots of log write behavior that tends to be smaller I/O. So to that end, we are doing 8K random writes against the 45 gigabytes of space that we're using for the first application. So we'll start that now, and as that process starts, you'll see the activity increase on the performance monitors. And again, this one is more representative of an OLTP load. So we'll let the load run for a little while, and as the activity picks up, once it stabilizes a little bit, you'll get a chance to see what happens when we add the second process. Now the second SQL I/O load will be representative of something more like a month-end report. So fewer users, but doing lots of reads, selecting all the data out of a database, analyzing it, whatever. And the block size is larger. So for the second I/O load, what we've done is we're using 64K block sizes. Again, 24 threads as in the previous with 3 devices spread across all 3 nodes. So that load is more indicative of read behavior. So you won't see as many IOPS. Typically in that kind of load, it's around 10,000 IOPS for this particular sample, and somewhere in the vicinity of 200 to 300 gig per second. Now, once this has all been running for a while, you'll get a chance to see this stabilize. So we see a fairly consistent performance across the graphs now as both applications are running. And what we're going to do at this point is start the desktops. Now again, this is the kind of situation where you would have 600 desktops simultaneously kicking off. So to that end, what we'll do is start 1 through 600 desktops all at the same time. You'll see the timer come on once the activity is started. And as each one of these desktops starts, you'll see next to it the little black window will show the Control-Alt-Delete or login screen. So the point is, now we see the profile change as that load is picked up. Again, to notice that the latency the latency curve on the very bottom of the screens is minimal, and the impact on the other screens, on the other application workflows, remain unchanged. So the point here is to talk about behavior of Flash, for example, in multiple or concurrent environments. One of the benefits that we get with Flash and solid state devices is we don't have to worry about I/O isolation. So again, with this configuration, what you're seeing is all of them actively going against the same storage nodes. Those LUNs reside on the same devices, and we don't have to worry about any share contention. So the peaks are pretty clear. Again, workload is consistent, and that's the goal. So the net result of all of this is, after laying out 3 fairly specifically heavy workloads against the environment, you'll notice that we haven't done anything that's really complicated management of this environment. What we've done is we've simply carved out arrays, carved out LUNs on the array, so each node has the particular storage that it needs for that application to run. That's it. So you're dramatically simplifying the overall workload, management of the workload, management and creation of the LUNs that you need to support that workload. Again, let's talk a little bit about that. In the case of the SQLite behavior, we took 3 LUNs, each 15 gigabytes for a composite of 45 gigabytes per workload. And in the case of the desktops, we have 3 LUNs, each at 1.5 terabytes, which represents the capacity we need for the 600 desktops. So as you can see, we should have a fair number of the desktops up and running by now. And you'll see the IOs are actually starting to tail off on the application. And as they tail off, you'll continue to see the desktops can run. Now, what we've noticed in the past is that it typically takes somewhere about 2.5 to 3 minutes for all of the desktops to actually power up. And again, the thing to bear in mind is when you're looking at this is that these are workloads that are running in conjacent or concurrent with each other, so and adjacent on the same physical devices. Little impact, minimized impact, continue to show total bandwidth against the application. So some quick notes just to bear in mind. The point of that whole exercise is to get us to the point where you can realize Flash offers you the opportunity to really consolidate your storage platforms in ways that you really couldn't before. Because the peak activity of this particular demonstration is somewhere around 200,000 IOs and around 2 gig a second. That's it. Now out of this 3 nodes that we have as available capacity around 325,000 and 3.7, almost 4 gig per second of total bandwidth. So again, fairly heavy I/O workloads, and we've only consumed roughly, a little better than half the total capacity of the box, and we've demonstrated that these 3 workloads can continue to run without impacting each other.